Welcome all. In this video, we will learn about resonance. Students will be able to analyze the frequency response bandwidth Q factor of RLC circuit. Resonance is the frequency response of a circuit or network when it is operating at its natural frequency called resonance frequency. For many applications, the supply is constant, that is defined by its voltage and frequency. Example, the supply of residential home is 230 volt and 50 hertz. However, many communication systems involve circuits in which the supply voltage operates with a varying frequency. To understand communication system, one requires a knowledge of how circuits are affected by a variation of the frequency. Examples of such communication systems are radio, television, telephones, and machine control systems. Resonance occurs in any circuit that has energy storage elements, at least one inductor and one capacitor. Under resonance, the total impedance is equal to the resistance only and the maximum power is drawn from the supply by the circuit. Under resonance, the total supply voltage and supply current are in phase, so the power factor becomes unity. At resonance, L, that is inductor, and capacitor C elements exchange energy freely as a function of time, which results in sinusoidal oscillations either across L or C, that is inductor or capacitor. Type of resonance are series resonance and parallel resonance. Resonance in series RLC circuit. Resonance is a condition in an RLC circuit in which the capacitive and inductive reactance are equal in magnitude, thereby resulting in a purely resistive impedance. The input impedance is as follows, that is, Z is equal to R plus j omega L plus 1 by j omega C. Here we can take j common, so R plus j into omega L minus 1 by omega C. So at resonance, the net reactance becomes 0. Therefore, omega LR is equal to 1 by omega RC is equal to omega R is equal to 1 by root LC. So, the frequency at resonance is equal to 1 by 2 pi root LC hertz, where omega R and the FR represents resonance frequency in radians and in hertz, respectively. Variation of reactance and impedance with frequency. At resonance frequency Fr, the power factor is unity, that is purely resistive. Below resonance frequency, the circuit is more capacitive and the power factor is leading. And above resonance frequency, the circuit is more inductive and the power factor is lagging. Next is quality factor. The sharpness of the resonance in a resonant circuit is measured quantitatively by the quality factor Q. The quality factor relates the maximum or peak energy stored to the energy dissipated in the circuit per cycle of oscillation. That is, Q is equal to 2 pi into peak energy stored in the circuit by energy dissipated by the circuit in one period at resonance. So, it is also regarded as a measure of the energy storage property of a circuit in relation to its energy dissipation property. Diagram shows the effect of frequency variation on voltage across R, L, and C.